Hi, you guys. I'm back with problem 5.25 from Young and Freedman's University Physics textbook. So I have so much on my mind, and let's see if I can remember to give you all my updates really quickly. So first of all, please don't forget to like and subscribe. Thank you so much for 1,000 subscribers, and I hope I can grow that some more. So if you find my videos helpful, please don't forget to like and subscribe. And I think tomorrow I actually become a YouTube partner because I finally have enough watch hours. So I'm so thankful for that. Thank you everyone who's tuned in to watch and left comments and likes and shares. So thank you so much for all of that. Little life update. The city I'm living in right now, the fall foliage is at its peak. So I'm so excited. Tomorrow morning, I'm gonna have I usually like to do a girls' day with like one of my friends, but tomorrow's actually the first day I'm like all by myself and doing like a day out, like a girls' day out, but just by myself. So I'm super excited to see the fall leaves and go to like a cute coffee shop and wear like my favorite fall sweater. Yeah. And oh my God, okay, yeah. So um, I have more chapter 5 problems. I know someone requested that a while back. I don't remember who it is. I have so many requests now. I'm so sorry if I haven't gotten to them yet. It's just my work is so busy that I don't have, the time that I used to. I used to work from home, and now I'm like working. I was about to say where I work. No, I'm working all day long. I want to protect my privacy, but yeah, I'm working all day long, and so now I don't have the time that I used to have. Plus, I'm living by myself too now, so I have to do things like cook and clean for myself. Yeah, I'm such a baby. Okay, going to do this really quickly. If I'm distracted, that's because I might like pause every now and then. I'm just trying to sell my Taylor Swift tickets right now. And so I keep getting text messages on my phone. So yeah, hopefully that's not a problem. Okay. So this problem that we're about to do, it is so beautiful. Okay. It's very demure, very mindful, very cutesy. You're about to see what I mean. Yeah, I just called this problem cute and you think I'm such a weirdo, but I said what I said because well, okay, you'll see. You'll see. Let's get to the problem and you'll see why this problem is just it's so elegant. The solution is so elegant. Okay, so the Trendelenburg position. Never heard of that. I don't usually like read like extraneous information, I guess, but yeah, the Trendelenburg position. I hope that's how it's pronounced. Okay. After emergencies with major blood loss, um, a patient is placed in the Trendelenburg position, in which the foot of the bed is raised to get maximum blood flow to the brain. If the coefficient of static friction between a typical patient and the bed sheets is 1.20, what is the maximum angle at which the bed can be tilted with respect to the floor before the patient begins to slide? Okay, so one of the reasons why I never really know what like if there's like a new vocabulary word, I don't really know what it means is because like obviously it's not like, relevant to the question. And so it actually gives us an explanation right over here. I think that's actually the most important thing right now, that the the Trendelenburg problem, or sorry, the Trendelenburg position is one in which the foot of the bed is raised to get maximum blood flow to the brain. Awesome. Okay, so that's the key information in this question. So now let's actually go ahead and do everything that we usually like to do. So let's draw out the problem. Okay, so we have some patient that has major blood loss, and we have this position that we're going to draw. And I'm going to use black for like the stretcher, I guess, right? And so this is the bed, right? Or actually, sorry, I need to change back to pen instead of highlighter. So yeah, this is like the bed, let's say, right? And the foot of the bed, so let's say like, yeah, this is the foot of the bed. It's raised to get maximum blood flow to the brain. So let's draw our patient. So let's just say this is our patient. Okay. And we're going to get, yeah, so through this, we're going to get max blood flow to brain. Cool. Okay, so if the coefficient of static friction between a typical patient and the bed sheets is 1.20. So we know that, mu s, right, static coefficient of static friction is 1.20. What is the maximum angle at which the bed can be tilted with respect to the floor before the patient begins to slide, right? So this is some angle, and we want some angle theta, let's say, right? So we want to know what's the maximum angle before the patient starts to slide off, right? Of course, because obviously, if this is the bed, right? If this is the bed and it's tilted, like this at this steep angle, right? Then the patient's literally just gonna like slide off, right? And that's not what we want. And if it's, we don't want it to be like not tilted either. We don't want it to be like flat either, because if we have like some sort of shallow angle, then we're not really getting that blood flow to the brain, right? So we don't want this and we don't want this. We want this right over here. We want this. Okay, so now let's talk about our knowns. So what are the knowns in this problem? The knowns in this problem are okay, so the knowns in this problem are mu s. Oh, well, that physics tutor, I was about to use my name, but oh, I thought you said this problem is so cute, so elegant, so beautiful, but we only have one piece of information. Yeah, that's all we need. Okay. And that's why this problem is so cool and so fun, and you're about to see, what we can do. Okay. So what do we know? Let's go ahead and dissect this image right over here, right? So again, let's say that we have let's draw all of the forces that are acting on this patient in this bed, right? So we have our patient right over here. What are the forces acting on this patient? So we have our theta, okay? So one, obviously, we have the force of gravity, right? Because we're on planet Earth. Then we have our normal force, which is this, Fn, normal force, right? And normal force is always perpendicular to a surface, right? When an object comes in contact with the surface, right? Okay. And now we also know that there is a force of static friction, which is this way, right? And if, we want to make this diagram even like, simpler, we can do something like this. We can say that, if this is our like mass, we have three forces. We have Fg, we have F, F mu s, right? Force of static friction. And then we have normal force, right? And let's have our coordinate system. So this kind of reminds me of a ramp, right? And with a ramp, we like to set up our coordinate system like this, right? So we'll say this is positive and this is positive, right? So we'll say, like, for example, yeah, we'll say this is positive and this is positive, right? Okay, so cool. Now that we have our force body diagram, we can go ahead and write down the summation of the summation of forces in the x and y direction. So let's say that this is our x direction and this is our y direction, right? So positive y, positive x. And let's go ahead and just write down the summation of forces, right? So actually, before we go ahead and do that, we can definitely note that, for example, this over here, that's definitely like in our, quote unquote positive y direction. Well, actually it is positive y because that's what we set it up. We said that's going to be positive y. So this makes sense, right? This also makes sense to be like, this is positive y, right? This is negative x. That also makes sense. But this is neither y nor x, right? This is just like at an angle in between both x and y direction. And so what we can do is we can actually go ahead and we can break down this into two separate components. We can break this down into an X and Y component, right? Because at the end of the day, if we can break down this FG into an X component and a Y component. So our component in the X direction, the positive X direction, is going to be, well, actually, it makes more sense if I draw it out here first, right? So this theta, using similar triangles, we know that this angle over here is theta, right? Because this is theta, and that means that this is theta too, right? This is not really a math tutorial, so if you need help with that, either figure it out from a different YouTube video or send me an email and maybe I'll create a video that's more specific to that. But anyways, okay. So this is theta, right? And theta, yeah, this is theta. And we know that FG is going to be FGX, right? And FGY are going to be FG sine theta, right? And then Fy is going to be Fg cos theta. All right. Okay. So now let's go ahead and write down our summation of forces in each direction. So I'm going to use blue. So in our X, right, the summation of forces in our X direction, we have, right, so we know that the patient is lying still, right? The whole point is that we don't want the patient to slide, right? And we know that if the patient isn't moving, that means that the forces balance out, right? Both in the X and Y direction, right? So we know that the summation of forces in the X direction are going to be 0. And also we know that the summation of forces in the Y direction are also, actually, I should write it this way. In the summation of forces in the X direction are equal to 0, and then the summation of forces in the Y direction is also equal to 0. Okay, but what exactly is that? What's the individual breakdown of those forces? And the breakdown is Fg. Okay, so we know that the force of static friction plus the force of the X component of the force of gravity, that add them together, that cancels out, right? Because if it didn't cancel out, that would make the patient slide, right? So sine theta is equal to 0, right? Oh, that's redundant. I don't need to write that down. And then we just do the same thing in the Y direction, right? So in the Y direction, we have also the patient isn't moving this way. The patient isn't like jumping up and down. It's not falling through the bed. It's not jumping upwards. So we know that Fn plus Fg, the Y component of G, so Fg cos theta is equal to 0. Now you might say, hey, wait a second. You made both of these positive, even though there's one of them isn't they're the opposite directions of each other, right? So yeah, that's true, right? And we can write that down in our 1 second. Give me 1 second. I'm gonna pause this. Okay, back. Sorry. Okay, so yeah, you can write them down. You can add the signs now or later. I'm kind of thinking of these as just the vector forces, right? So when you sum them together, they're equal to 0 because one is positive and one is negative, right? But you can be more specific with that. Okay, so all right. So now what are we trying to do in this question? We are trying to figure out what is this theta, right? What is this theta right over here, which is the same as this theta right over here? What is that? Okay, so if we want to figure that out, let's go ahead and figure that out. One second, getting a text. Okay, sorry again. I'm back. Okay. So just to recap, I don't know if I already said this, but this is sort of like the like vector statement, right? And we can use like if we wanted to actually use like write it down as sort of like a more scalar sentence. I don't even know if that's like the right way to explain it, but then we would incorporate positives and negatives depending on which direction each force is pointing, right? Okay, so um, because we're solving for theta, let's go ahead and use this first equation right over here, right? Okay, so um, we know that this okay, you know what, actually, let's go ahead. I don't like how I did that. I'm going to actually rewrite the like this with signs in the first place. I think that's actually better. Okay. So I'm not going to pretend it's like I'm writing down vectors. I'm actually just going to write them down I'm going to write them down with directions, right? So what do I mean by that? What I mean is that this force of static friction is pointing in the negative x direction, right? So like that's pointing this way, that's minus. So I'm going to put a minus right over there. And then this FG sine theta, that's in this direction, and that's actually in the positive x direction. So that's going to keep its positive, right? And then for this right over here, Fy, Fn, like, yeah, that's in the positive y direction. So we're going to keep that. And then Fg cos theta, like, that's in the negative direction. So, like, that's what I mean by they cancel each other out. Like, it's not wrong to write it the first way, but you just have to keep in mind that the signs, but the sign would be like included within the static friction force, right? But this is way more intuitive. I think this is way better. Okay, so we have that. This is positive, this is negative, and this is positive. Cool. Okay, so now we're solving for theta. Let's start off with our first equation right over here, right? And we can rewrite this as the force of static friction is equal to Fg sine theta, right? And now all we need is to solve for isolate for this theta, which, you know, that's easy. Um, let's do that. F mu s over Fg, right? Is equal to sine theta, right? And what exactly is F mu s? Well, that's normal force, Fn, mu s over Fg, and that's equal to sine theta. Okay, but hold on a second. To get Fn, uh, or actually, yeah, well, okay, actually, first let's write down Fg. We can write that down as mg, right? So that's force of gravity is just mass times gravity, right? And Fn, well, how do we get Fn? How do we simplify that further? Well, we can use this equation right over here, right? So Fn is equal to Fg cos theta, right? So we bring this minus side, this like minus term to the other side and it becomes positive, right? Because we add Fg to both sides. And we can replace this Fn with this Fg cos theta, right? So then Fg cos theta, or like mg basically, right? Doesn't matter. I only changed that to mg because I already simplified here, but it doesn't matter if you keep this as fg, then you'll keep this as fg. But anyways, okay, so Fn is equal to mg cos theta. Mu s is over mg is equal to sine theta. Do you see it? We can cancel this out, right? And how cute. Now we end up with mu s is equal to sine theta over cos theta, right? Which means we end up with, okay, let's bring it back over here. And I'm just going to do it in a different color so that you can see a little bit better. But that means that mu s is equal to sine theta over cosine theta is equal to tan theta, right? And that means that the angle we were looking for all along, it was just simplified to theta is equal to the uh, tan inverse of mu s. Okay, I actually haven't written this such a long time. I hope that's the right way to write it, right? Tan inverse ms. I'm just gonna like double check. Okay, yeah, sorry. So yeah, I haven't done like trig in such a long time. Besides literally when I do these videos. So yeah, I forgot how to write tan inverse. But okay, so yeah, theta is equal to tan inverse mu s, right? And that, look here, that's the only piece of information that we're like actually given in the question. So that means that theta is equal to well, I already said that, but theta is equal to tan inverse of 1.2, which is 50.2 degrees, right? That's just, and because we're only given, oh yeah, 50.2 degrees. That's the answer. So this bed has to be at an angle of 50.2 degrees for that's the maximum angle at which the bed can be tilted with respect to the floor before the patient begins to slide. That's our solution. See how cute and beautiful that solution was? So cute and beautiful because everything just canceled out in the end. Awesome. Okay, I hope that was helpful. If it was, please don't forget to like and subscribe, share with your friends. Thank you so much for watching and see you next time. Bye.